So question number 2 on your problem set asks you to use table 16.3 to answer the following questions. Right? It says, what is the value of delta G naught for the reaction of ATP plus glycerol, giving us ADP plus glycerol 3-phosphate? Right, so that's the first part of the question. Then it asks you a couple of sub-questions that we'll come back to once we finish that first part. All right, so how do we figure out the value of delta G0 for a reaction? Well, in that table, basically we have a bunch of energies of hydrolysis. So we're going to use those to calculate the delta G0 value for this complete reaction. So our net reaction is ATP plus glycerol, giving us ADP plus glycerol 3-phosphate. So we want to break this combined reaction down into 2 different hydrolysis reactions. So in one case, our ATP, all right, it's getting converted to ADP. So we want to look in that particular table, and we'll find ATP getting converted to ADP and phosphate. And that reaction, the hydrolysis of that ATP, gives us a negative 30.5 kilojoules per mole. Now the other metabolite is our glycerol going to glycerol 3-phosphate. All right, so if we look at our table, we'll see the energy of hydrolysis of glycerol 3-phosphate going to glycerol and phosphate, but we won't see this reverse reaction. All right, well, all we need to do basically is take the energy of the hydrolysis of this and flip it around. So we're going to flip the reaction, which means we're going to change the sign on delta G. So the delta G for glycerol 3-phosphate getting hydrolyzed is negative 9.2 kilojoules per mole. Well, if we're going the opposite direction, it's going to be a positive 9.2 kilojoules per mole. All right. Well, once we've done this, all we're going to do is take those delta G values and add them together, and we'll get our final answer of negative 21.3 kilojoules per mole. All right, so back to our questions then. All right, the first sub-question asks us, based on our answer in A, is this likely to be a fast reaction or a slow reaction? Explain. All right, well, this is a little bit of a trick question. So what determines the reaction, the speed of a reaction? Is it how exergonic or endergonic it is? All right, the answer is no. All right, the speed of the reaction is unaffected by whether the reaction is going forward or reverse, or how much energy is being released or gained by that reaction in the net form. All right, what does affect the speed is the height of the hill, the activation energy that we have to cross to get from reactants to products. All right, the part A there, that delta G0 value, that tells us about the energy difference between the reactants and products. It says nothing about transition state energy, so we can't actually determine if this is a fast or slow reaction because we're not given any information about the activation energy. We're only given information about the final energy change of the reaction. All right, the next part, for the reaction in A, what is the equilibrium constant for the reaction? All right, so this question, so we just determined our delta G0 value in part A. All right, this is asking us now to use that delta G0 value to determine an equilibrium constant. Well, to do that, we're going to remember this equation. Delta G naught is equal to negative RT times the natural log of KEQ. All right, so if we're going to rearrange this around, so we want to get KEQ by itself, so we're initially going to divide by negative RT, and we'll have natural log of KEQ is equal to delta G naught over negative RT. All right, well, to get rid of the natural log, we take e to the power of everything on that side. So we end up now with KEQ is equal to e to the negative delta G naught over RT power. All right, well, we can plug in the values we have. So we have negative 21.3 kilojoules per mole for our energy. So we want to find a gas constant that has units of kilojoules per mole and Kelvin. So that's 0.008314. And then temperature. The temperature was not given in this problem, but I am giving you delta G naught, which means that we're under standard conditions, which is 25 Celsius. So that would be 298 degrees Kelvin under standard conditions. So when you compute all that, the exponent is just 8.6. And so e to the 8.6 power is 5,430. All right, now our last part of the question here, for the reaction in A, what is the value of delta G? All right, there's no naught on that. If the concentration of all the reactants and products are 100 micromolar at 16 degrees Celsius. All right, well, so under any sort of non-standard condition, all right, we're going to use this equation right here. Delta G is equal to delta G naught plus RT times natural log of Q, is the way it's usually written. Well, Q it looks like the equilibrium constant, but it's using the actual concentrations rather than the concentrations at equilibrium. All right, so, well, we know delta G naught, we can plug that in there, negative 21.3 kilojoules per mole. Now, for this part here, all right, we could plug in R with kilojoules per mole and T, that's 16 degrees Celsius. We'd have to convert it to Kelvin, but we could plug that in. But let's focus on the stuff inside the logarithm there. So the question says that all of our reactant and product concentrations are 100 micromolar. All right, so basically we're going to have 100 times 100 over 100 times 100. All right, that's going to be 1. And the natural log of 1 is 0. So this whole portion over here on the right becomes 0. So our delta G value then is just going to be that negative 21.3 kilojoules per mole in this particular case.